So what we were working on is root finding techniques. And essentially what we are doing is solving for x, to find x that satisfies this equation where f x is a function, a generic function in x, and that is equals to 0. So we are trying to find the values of x which satisfies this equation. That satisfies this equation. Now we are doing that in a numerical manner, in the sense that we do not have any access to any analytical formula. Just like if it is a quadratic equation, we discussed that you know how to solve for the roots of a quadratic equation. But if fx is a very generic nonlinear function, for example, fx is, let's say, exponential x plus sine 2 pi x plus x minus a constant, let's say 2. So this is a very generic function for which I do not know what will be the value of x for which fx will become equals to 0. And this is basically the system, or basically the function that may arise where you're doing some sort of a curve fitting technique and you are trying to model a physical system where the function response or the response is nonlinear, and you're trying to find the roots of the function, or trying to find where the function crosses the x-axis. So in those situations, you need to find the roots of a function. And here it is a nonlinear system. So we are basically trying to see what are the numerical techniques that are available to us to solve this system where fx equals 0 can be solved for specific values of x. And we saw that for root finding techniques, there are two types of techniques: bracketing methods and open methods. Bracketing methods are the methods that actually bracket the root. So it basically starts with an interval. It starts with an interval x lying between, let's say, x0 and x1, such that fx0 times fx1 is less than 0. So this condition guarantees that the function, this fx function, this function, generic function, crosses the x-axis. So this is your x0. This is function value at x0. This is x1. This is the function value at fx, and this is the function value at x1. This generic curve is your function fx, and this is your x-axis. This is y-axis, or you're plotting fx on this axis. So for bracketing methods is a class of numerical technique where you start with an interval such that it brackets a root. The root actually lies within this interval, x0 and x1. And there are two types of bracketing techniques. One is called as bisection method. Bisection method. Another bracketing technique is known as regular falsy or false position method. Regular falsy or false position method. So that much we actually discussed in our last lecture, at the end of the last lecture. So before we actually move forward and discuss further, that we also discussed a bit about what the bisection method is, but we will actually do it again so that you actually know what each method is and how they are different. So we will start with the details of the bracketing methods, and if time permits, we'll also see open methods. And open methods are, there are three methods we are going to see: fixed point, Newton's method, and secant method. So if time permits, we'll also go through all these three. But before we actually go into the details, any questions, concerns, and issues, guys? Is everybody good so far?
Yeah, I think we're good.
Yes, Professor.
Yep. Let me know if you have any questions, any concerns. So I have not mentioned, I also posted the syllabus in the Beachboard, so you probably have access to it. So that the most important part that is that you will be referring to is the grading criteria. So you can basically look at it and see how the gradings are distributed throughout uh, the course or throughout the duration of the semester. So we'll have homework, midterm, and final exam, and that's how the gradings are distributed. Textbooks, we have already discussed about it, and pretty much that's it about the syllabus. So coming back to the lecture content, so we will now go and see how bisection and regular falsy methods work, and which are nothing but a class of bracketing methods. So no questions so far, right, guys?
Yeah, none so far.
So far. Okay. So what happens in bisection method? Let me. So so let's say I have a function, a generic function which varies as it as non-linearly as it can. I mean, there is uh, no way I can predict the variation of it, or basically it's the arbitrary shaped function. So it can be any non-linear. It can have any non-linear response or non-linear shape. Now, when I say bracketing methods, we basically are starting with this interval x0 and x1, where basically the starting point is by the knowing the physics of the problem, or by uh, knowing the generic nature of the physical problem that you're trying to solve. You know exactly the root have some will have some bound. So it basically the root lies between certain bounds. So within that bound, if you know the root lies, so you straight away know at the very beginning that what is your interval length, or what is your starting interval. So starting interval is basically you define this as A, and let's say this is B. This is function at fa, and this is function at point b, and you know by at the very beginning that fa times fb is less than 0. That's known to you. So at the very first step, what you are going to do is you are going to bisect this interval. Bisect this interval is to find the midpoint of the interval. So to find the midpoint of the interval, what you are going to do, you take the average of uh, these two numbers. So you basically find a point C, where C is nothing but the midpoint of these two starting points, A and B. And what you do, you actually try to find the function f function value at this midpoint. So you evaluate that. And when you evaluate that, then what will happen? So let me say here, the first iteration, the first step, interval for getting the root is from A to B. For the second step, what you are going to do, you bisect the root, you find the midpoint, and you evaluate the function, and then you check whether fa check if fa function at A times function at C is less than 0. If it is less than 0, that means the root will lie, then the root will lie within A and C. Else, the root will lie within C and B. Does that make sense? So what you are doing, you are basically starting with this interval A and B, and then at the second step, you actually bisect this or find the midpoint of this interval, which is C, and try to find what is the function value at point C, which is f of C, function evaluated at point C. what you are going to do is you are going to check whether the sign of fa times fc is less than 0. So you're going to multiply this value with this value and see whether it is less than 0. Now in this specific diagram and this specific plot, clearly this is not the case. So that means the root is not going to lie between A and C, but the root is going to lie between C and B. So what we are checking is if FA times FC is less than 0, this is less than 0, which is not, then what we are going to do, the root lies between C and B. So for the second step, the interval length for finding the root is equals to B minus A divided by 2. Does it make sense?
Yeah.
To everybody. I mean, if you have any doubt, any questions, any confusion, can you please ask and let me know which point you have lost or which part or which at what step you actually lost it. So is everybody good and is everybody okay so far with me?
Yes, Professor.
Yep. Okay, great. So let me randomly pick a student from the list here. Let's say Ethan. Are you there?
Yes, Professor, I'm here.
Great. So Ethan, can you tell me that what will be the interval length for my third step? So when I started the first step, my interval length was B minus A. So when I started, the interval length was length of the interval. When I say interval is length of the interval or the bracket or length of that, the point, a distance between 2 points where the root lies is given by B minus A, isn't it? Right?
Yes.
It lies within this distance, which is B minus A. In the second step, when I actually found the midpoint and check, and I found that the interval length has been reduced by half, B minus A by 2. You are with me so
Yes.
far?
Yes.
So can you tell me what will be the interval length for the third step? So what will be the third step? Okay, I am trying to help you here. This is first point and second. This is the starting point, A and B, right?
Yes, sir.
First step. And the second step, I found a midpoint. And this is the second, at the second step, I found the midpoint, and I'm then saying that either the root lies within this interval or it lies within this interval. So by using this criteria, I found that root lies within this interval. And in this interval, the length is B minus A over 2. Agree?
Yes.
So in the third step, what you are going to do, you are going to take the midpoint of these two again. So you are going to bisect these two intervals, C and B. So it will be clearly somewhere over here, right?
Yes.
Right? So what will be the interval length in third step?
B minus C over 2.
Actually, B minus A divided by 2 square. Basically, you starting with this interval length and you are again making it half. You are basically reducing the interval length by half for every step. So at this step, the interval length was B minus A, which is this much. After second step, interval length becomes B minus A by 2, which is half of this. So you basically take this length and you half it. So now it is half. And after the end of the third step, the interval length will again become half of that. Do you see what I'm saying?
Yes.
Yeah. So the every step, what happens that the interval length after nth step, the interval length is given by B minus A divided by 2 raised to power n minus 1. Does it make sense to you guys?
Yes, Professor.
Yeah, are you guys able to see? And if not, let me know if you have any questions or concerns. So what it is saying that what we are going to do is for every step we are going to half the interval length. So we start with this much length, then we half it, then we again half it, and we keep on doing that until we actually reach very much close to this value, which is the root. So we are not going, we may or may not be going reaching to the root exactly, but what we are going to do will be actually using these steps, we are going to be very, very close to the root where your fx equals 0. So what happens that the error in that estimation or error in the root, or basically what you are going to see is that x n plus 1 minus xn is given by b minus a divided by 2n. Basically what it says that at the n plus 1th, at the n plus 1th step, the value of x, which we are saying that it is basically the going to be very close to the root, minus the x value at the previous step is given by this specific interval length. Now why it is n minus 1, because I'm going to the n plus 1th time step. So that is why it is n here. So what it says that after nth step, the error in the estimation of the root is given by this. So if you have to determine at what step you need to stop, how will you determine that? Is my question clear, guys? Or if not, I'm going to repeat again. First, let me explain what I'm trying to say here. We start with this interval, and we know that within this interval, the root lies, which is clearly the case by using this condition. And for every step, we are basically reducing the interval length by half. So we start with this interval length, and then we are basically reducing it by half, then again by half, and we keep on doing so. So while keeping on doing this type of reducing the interval length by half, where do you think, how we will know that we have to stop now? How long we should keep on doing this? Is my question clear now, guys?
Professor, for the n step, is it going to be the n interval length, right?
Yeah.
So,
sorry, I think your voice has got disconnected. You got disconnected. Can you explain? Can you ask again, please, your question? Yeah, is there anybody was asking any question?
Well,
can you guys hear me?
Oh, go ahead.
Yes, now I can hear you.
Go ahead.
Go ahead.
So my question was this, okay, so when you say the n step, would that be the n interval, right?
Yeah.
Okay, so for the first interval, you'll be b minus a divided by 2.
No. That is the first when you're starting step. The n is equals to 1. That is the first step when you're starting. Then n equals 2, second step, n equals 3. And now when you have n equals nth step, you actually reach this.
Okay, I see what you're talking.
So when you start the very first iteration, very first time, very first step, at that point, the interval length was b minus a.
Okay.
Second step, it's b minus a over 2, and so on and so on and so forth. Okay. Now, my question to you guys was that how long should I keep on doing this? When do I know that I have to stop? Because this is just like a computer algorithm. So you are just going to implement this and code it in MATLAB. If you're comfortable with C, you can do that in C. I mean, whichever language you are comfortable at. So you can do that. I mean, you don't need to even implement in computer. You can do the calculation because it's just a simple algorithm. You don't need to do too much of computations. So you can do the computation as well. But my question is how long you have to keep on doing that? How will you decide?
You set up a tolerance.
You set up a tolerance for what?
For because f of f the root will equal to c. So you want to, like, if you want to keep it within like 10 decimal places of 0, or
For what? For the function value?
yeah, for the function value.
Great.
Or
So that is one. So there, let me tell you, there are 3 stopping criterias for any algorithm which actually uh, is going to be implemented or going to be, going to be implemented in a MATLAB code or any C programming language or in any other language. So any numerical technique, you will see that it involves a lot of steps or iterations, and there are 3 stopping criteria. So the 3 stopping criteria that we are going to discuss today are, one of them, as you just rightly said, the first criteria is that you take the function value at nth time step and see whether it is less than the tolerance value.
Professor, yeah.
So you are going to pick the value of x at nth time step or nth step, and you see that that function has to be less than the threshold, because what we are doing eventually, we are basically trying to find a root. When we are saying trying to find a root, we are going to solve if x equals 0. That's what we are trying to solve. So that means our objective is to find the value of x such that if x becomes equals to 0, isn't it? Right? Now, if we are, I mean, if I say if we are lucky enough to find the exact root, then you will have fx exactly equals to 0. But this is seldom the case because you are trying to bisect the root. So you will be very, very close to that. You may not be actually reaching the exact value of the root. So you'll be very, very near to that root. And when you will be very, very near to that root, that what will happen? The function value will be close to 0. So the function value will be very, very close to 0. So you can pick a number, threshold maybe 10 is to power -6 or -3, whatever number you would like to choose. And if you can apply or consider this criteria, that means the function value at that point is very, very small, which means the x is much, much closer to the actual root. Does that make sense? Are you guys able to follow what we are doing here?
Yeah. Would the second method for stopping criteria be the number of iterations?
Perfect. Number of iterations. So you can basically say that the number of iterations should not exceed, let's say, 1,000. So I want a condition that I don't want to continue beyond 1,000 steps. So whatever the root, wherever the root actually reaches at 1,000 step, I will solve. So I want to pick a technique, or I want a method such that I need to find roots before the 1,000 steps, because what happens, for every time step there are some computations involved, and once there are computations involved, that means it involves the computation time, it involves basically the computing resources gets occupied. So basically you want to reduce that amount of time, completion time. So you don't want to exceed beyond 1,000 or maybe some other number that you can pick up. So that is one of the other criteria that can help you to stop. What will be the third criteria?
We can check the interval and then we can decide how many n time you can get into a very small half interval that you can use, and by that you can predetermine the how many steps you can get to that point.
Yeah, so if I actually go back, I was basically saying that after nth step or n+1th step, it is basically the error is defined by, or how close you are getting to the root is defined by this specific expression, which says how much close is the interval length. Is the interval length is getting shorter and smaller and smaller and smaller. There is a limit when the successive interval lengths are not that much different. So let's say b minus a, for example, just for the sake of seeing how the numbers work here, let's say, for example, a equals 1 and b equals 3 and n equals, let's say 10. But what will be the interval length in that case? Can you quickly calculate it, please? At the nth step, the interval length is given by this. This is for the n plus 1th step. So at the nth step, interval length is given by this. So if A is 1, B is 3, N is 10, that means I'm at 10th step. What will be the interval length in number? Can you guys let me know after calculations using your calculator?
1 over 256.
What is that number?
(1.953 times 10 to the negative third).
Negative 30, you said, right?
Oh, no, third.
Third, okay. 1.95 E minus 3. That's correct, right? Right? That's what
I got.
So when n equals 11, what will be the interval length now?
Different answer.
9.765 times 10 to the negative fourth.
So you will see that as the interval length, as you increasing the number of steps, the interval length is getting shorter and shorter and shorter. Does that make sense to you, what I'm saying? So is it making sense, guys, what I'm saying here? That as you keep on increasing the number or the nth step, you will see the interval length where the root lies, which is this circle, which I'm plotting here. This circle has got two, if I zoom this circle, I zoom this circle and I'm plotting it like this. So this is your actual root. This is your x n and xn minus 1, the two values of x. So you can either select this value, which is more absolute value of f of xn, that can be less than epsilon, or you can basically say that this diameter, which is xn minus xn minus 1 or xn plus 1 minus xn, whatever is that range you are going to select, that should be less than epsilon. So either this entire range is less than a threshold, the error is less than the threshold value, or the function value is less than threshold value, or the number of iterations is less than the maximum number of iterations that needs to be, that is a constraint that needs to be considered. Does that make sense, guys?
So the final stopping criteria is the interval length, right? So because the interval,
yeah, interval length. So this interval length has to be less than the threshold value. So there are three criteria, stopping criteria, and generally people use the first two criteria, combination of two. In the textbook by Dr. Esfandiyari, you will see that this criteria is used, and all of them basically will try to get as close to the root as possible. If you satisfy any of these three criteria, you are going to get as close to the root as possible. So any of these three criteria can be used by itself or a combination of two. When you are going to see a combination of two, generally you are going to incorporate at least one. This condition should be the number of iterations should be less than the max. And then you can pick either this criteria or you can use this criteria. Does that make sense, guys?
Yes, Professor.
Any questions so far? So you guys are good with the bisection method, right?
Yes.
So now we are going to see another bracketing method, which is regular false, your false position method. So what happens in false position method? It is another class of bracketing method.
Quick question, Professor.
Go ahead.
So for the first method, basically we're getting as close as possible to the exact
Yes.
solution.
Yes.
But if we don't know what the exact solution is to solve that equation, how do we know that we're close enough?
So that is given by this condition that your function value is very, very close to 0. So the exact solution means the function value is equals to 0, exactly equals to 0, right? But if you do not know that value, what is x, this x is basically the actual root. So let me call it x naught. So
Oh, okay. I got it. I think I got it.
got it? So
Yeah, thank
this
you.
is the stopping criteria will ensure that you are going to be very, very close to this value. Because other than this, function value will be very, very higher, larger in magnitude. But as you reach towards this value, the function value will be basically reaching 0.
Thank you.
Yeah, thanks, welcome. I'm just calling it as XR. XR is the root, actual root. Why am I writing root?
Professor, in method 2, can you repeat what the M stands for? I sorry I missed that.
M is the total number of iterations, the max number of iterations. The maximum number of iterations that you would constrain your algorithm to run up to.
Oh, thank you.
Yeah. Okay, so false position method. In false position method, what we do, we do not bisect the root, but again, we are going to, so let's say the function is, this is your fx, and this axis is your x-axis, this axis is your function y, which is equals to fx. This is the generic function. This is the actual root. So here also you start with the interval where you know the interval actually brackets the root. So you know fa times fb is less than 0. But thereafter, you do not actually bisect the bracket or bisect the interval. First step, interval root lies within this interval, and the length of this is b minus a, interval length. Just give me a second. I'm seeing some chats here. Okay. Okay. So the first step. Now what we do here, we join these 2 points with a straight line. And when we join this with a straight point, we find what is the intersection of that straight point with the x-axis. Does that make sense, guys?
Yes.
Yeah. If you understand that part, let me pick a student randomly from the list of attendees. Michael. Michael.
Can you hear me?
Yeah. Can you speak a bit louder, please?
Yeah.
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 So, yeah. So if I know the x and y coordinate of this point, I know the x and y coordinate of this point, I want to pass a straight line. Can you tell me the equation of the line that passes through these 2 points?
So I mean, you would just use the typical mx or y equals mx plus b, and then
yeah, y equal to mx plus b, but the easiest form, yeah, that's correct. The easiest form is what you can do is, if you know these 2 points, you can use this form generally.
Oh, yeah.
Okay, where this is basically your slope of the line. And what x1, y1 and x2, y2s are, it is basically, this is your x2, y2, and this is your x1. Is it okay, guys? Everybody is with me? Yeah?
Yes, Professor.
Yeah. Now, can you help me to say what will be x1 and what is y1 in terms of a's and b's? Let me ask, actually. That will help to help the people to understand. Can I ask Anthony? Anthony?
Can you hear me?
Yes. So can you tell me what will be x1 and y1 in terms of a and b's?
So your y would be your f of a.
y1.
Yeah.
Okay, and what is x1?
And your x1 would be just a.
A, correct. Okay, great. Thank you. Can I ask Javisa? Javisa. Okay. Can we have Farhan? Farhan Alam. Okay, you guys seem not to respond. So that's good.
I can answer, Professor. X2 will just be B.
Okay, so x2 will be b and y2 will be f of b.
Yes.
Plug and play in that, what you will actually get, y minus f of a, x minus a, fb minus fa divided by b minus a. And that basically gives me y as f of a plus x minus a, f of b minus f of a divided by b minus a. So that is what I will get as an equation of this straight line. Now in this equation, when I'm drawing the equation of straight line, what I'm interested to find is when this straight line crosses this x-axis. When this straight line crosses the x-axis, what will be the value of y in that case? Any volunteer?
It would be 0?
0, yeah. Because at that point, I'm interested to find my point C. So imagine, or basically if you know that in the bisection method, we are finding this point C as a midpoint of A and B. So we are just taking the midpoint of A's and B's. But here in the false position method, we are interested to find the point C not as a midpoint, but when this straight line which joins these two endpoints crosses the x-axis. And this is the point where this is a point at which the y value is equals to 0 for this straight line. So if this is the equation of straight line, I put y equals 0, then in that case, x will be equals to your c. So if I solve for that, what I will get is x minus a at y equals 0 is equals to c minus a is equals to minus f of a times f of b minus f of a divided by b minus a. And if I solve for c, it will be a minus f of a fb minus fa divided by b minus a. So I can basically stop, or I can basically keep on simplifying it to find what is the value of c I will get. So you can simplify it further, but I'm just stopping at this point. And this point basically tells me that this is the value of x after the first step. So for the second step, so this is your first step, you start with this interval. The second step will be the similar. Second step, the root either lies between a and c or c and b, where the value of c is given by the value we solved here. Does that make sense?
Yeah, and then you would just multiply the two new values to determine if
Yes,
it crosses
yes.
the axis, correct?
So once you found this c, then what you are going to do is you are just going to see whether f of a times f of c is less than 0. If that is the case, then the root lies in this. Or if f of c times f of b is less than 0, that means the root lies in this interval. So a root will lie either in this interval or in this interval. So now once you see that the third step will be the same, you actually find f of c and you join the straight line now again, and that way you are going to reach to the root very, very fast, or very, very quickly as compared to the bisection method. Maybe if the bisection method takes 6-7 steps, false position method will take 2 to 3 steps to reach closer to the actual root. Let me know if it makes sense, guys.
Can you please scroll back to step 1 just to finish? I didn't get the last part to write it. Yeah. Thank you.
Are you guys fine?
Almost done, Professor.
Yeah, okay. Take your time. So if you understand this part, then we will actually move towards the open methods. Open methods, basically Newton's method and secant methods, and we'll come to fixed point method later. But the idea with the open methods is now you don't need to worry about, now you don't need to worry about 2 points where brackets are root. You basically can start with only one initial guess and you can start working towards reaching your solution. We will just see that part in a second. So let me know if you are done writing this. I mean, these are all in your textbook. I'm just going through this so that you actually understand the basics behind that or what actually they mean.
Is this all still chapter 11, right?
Everything is chapter 11 right now.
Okay. Professor F, is it possible to go through an example, actual example of the method?
Actual example of the method. Surely we will do that when we will doing the MATLAB assignment in the next lecture. So we will take one specific example and then we will go through all the methods basically. Regular, false position method, bisection method, and do that. It is to do that you are using hand because it will take a lot of time and a lot of computation and you guys have to do the computation. So it will become easier if you have the MATLAB code in front of you. You can change the values and it will give you the answers and you can look at it how it works. Okay, so we will take the examples in the MATLAB class on Thursday. Okay, guys?
Cool, thanks.
Yeah, welcome. So this is what actually completes the discussion about the bracketing methods. Now we actually move to open methods. Open methods means we do not need to know the interval in which my root lies. So I can start with any x value and we can slowly move towards our root. So we will first start with Newton's method. So this is basically a class of open methods as well for root finding. So we start with Newton's method. What Newton's method says that, let's say you have a function, any arbitrary shaped function again. You start with, here we start with x initial guess. Any guess, it can lie here, it can lie here, it can lie anywhere. So I just take arbitrary as here and that will be your initial starting guess. And for that initial guess, since you know the function expression of the function, you also know what is f of x naught, what is the starting guess for that starting guess, what is the function value. So what you will do at the first step, you draw a tangent or find a tangent or to the curve for the first initial guess. So first initial guess is this, and this curve, I draw a tangent to this. This is a line which is a tangent to this function. And this line is basically f prime x naught, because this is f prime x at x equals x naught. F prime x basically means slope of this function at x evaluated at this point x naught. So this is the tangent to the function fx. And then you find the intersection of this tangent line with the x-axis. And for that, wherever that intersects, that becomes your next iteration value, next value of x. So what we have to do is, if we keep on doing that, if I again draw a function value and try to find the tangent, I actually receive this, I will reach at there, then that will be your x2. Then again, I will draw a tangent and I will actually come back to this, and slowly I'm going to move towards my root. Does that make sense, guys?
Professor.
Yes.
Wouldn't I'm kind of confused by that because wouldn't f prime of x naught be equal to 0 because f x naught is a it would be f x naught is a constant, right?
No, so I'm not taking a derivative of f of x naught. So for example, let's say f of x is equals to sine of x. So when I'm saying f of x naught, it is basically means sine of x naught. I'm not taking a derivative of this, but I'm taking a derivative of this. So f prime of x is cosine of x, and then at x naught, f prime of x naught is cosine of x naught.
Oh, okay. All right.
Okay.
Yeah.
So this is f prime is not basically obtained from this. It is basically obtained from here.
Okay.
Okay. So let me actually go through the steps. Probably it will be easier. So starting is the initial. So this, let me know what point you are basically not following. So I'm just again reiterating only the first few steps. So this is your function. This is a generic function, which can be any type. It can have sine, it can have cosine term, it can have exponential term, it can have x raised to power cube, x raised to power 5, whatever form it may have. And what you are going, or what the objective for us is to find the value of x such that absolute value of xn at after nth step should be less than the threshold value or tolerance level, which is for most of the cases you can take it as 10 raised to the minus 6. So if you are satisfying this criteria, that means you are very much close to the actual root. So that is what we are interested to find, or we are interested to find the value of xn. So for the very first step, I start with a random guess, initial guess, which is x naught. And I found my function value fx naught and tried to find the slope, also find the slope. And when I actually write the equation of this line and I say where it is intersecting, I would like to find what is the value of x1. So it will be the same step we have done for the false position method. But now what I'm going to do is I'm going to write it like this. Let me know if you are understanding this much expression or this equation. And let me know if you have not followed it. Is this expression clear to everybody here? Yeah, no, yes, no. I would appreciate any response, any feedback.
Yes.
Yes, Professor.
Yes.
Oh my fucking. Fuck these guys. Yes, Professor.
Just a word of caution, no expletives during the class. So please
Apologies, Professor.
respect your fellow classmates as well. So no expletives to be mentioned while you are speaking on your speaker.
Wait, Professor, so what happens when there's when it passes the point, when it passes the 0 point?
When it passes, sorry?
Yeah, when it passes the when x, like x to the n, if it passes the like the f of like when the function equals 0.
I'm not following your question. Can you?
Yeah. X1, x sub 1, that's before the location.
Yeah.
That's before the location equals 0.
Yeah.
And then x sub 2 is after the location equals 0. So what happens after that?
So what will happen after that? This technique guarantees the convergence that you actually keep on. If you take the tangent again and you find the intersection, you find that the slope of, the tangent line will be crossing the x-axis, which will be much nearer to the root. So the x3 will be again coming back to this point.
Okay.
This thing. So you're for depending on at different times as you keep on oscillating till you actually come to this radius where the function value is much less than tolerance value.
Professor,
Yes.
so essentially the f prime of x of n will eventually converge to f of x such that it meets
No,
at 0?
no. F prime x can have any value. So for example, let me actually take one specific example. So let me say this is my fx, for example, okay? Now, the root of this is here. This is the root of this equation, right? Where f of xr, this is your xr, is equals to 0. Are you with me?
Yeah.
Yeah. Now, what is f prime xr at this point? Is it 0?
No.
No, right? F prime xr basically is like this. So it has got a certain slope which has basically get some value, positive value. It may be 45 degrees, 30 degrees, whatever it is. So f prime xr is not equals to 0.
Okay, yeah, I see that.
You see what I'm saying?
Mm-hmm.
Great. Any other questions, guys? So my original question was, is everybody in the class understand this form?
I didn't understand, Professor.
You do not understand it. So that's good to know. And that will help me to explain it further. This is basically an equation of a straight line. Equation of a straight line having slope f prime x naught and passing through the point x naught and f of x naught. Now, is that making some sense? Equation of a straight line which has a slope fx naught, which is m, you can write it as m. Or if you remember that y minus y1 x minus x1 is equals to m, that is also an equation of a straight line which is passing through these 2 points x1 y1, which is x naught fx naught, and having a slope m, which is f prime at x naught. So this is basically nothing but an equation of a straight line. This is the equation of this tangent line. Now, if this is the equation of a tangent line, I am interested to find my x1. But before I actually go and explain that, was it Ethan who asked this question?
Yes, I asked, Professor.
So did you get it or are you still not getting it?
I understood right now.
You're understanding it.
Yeah.
So if you have understood it, like, can you answer the following step, that how will you find x1, which is the line crossing this x-axis? How can I use this equation to find x1? So this is the equation of a line, and the line crosses this point where what will be your y value at this point, Ethan?
0.
0. And what will be x value?
X1.
X1. So if you put y equals 0 and x equals x1 and solve that for x1, you can see what it will look like. So I'm going to do the same thing. I will put y equals 0, x equals x1. And then when I actually solve it, what I will get is x1 is equals to x naught minus f x naught divided by f prime x naught. And you will see that x2 will be x1 minus ff x1 divided by f prime of x1. And so on and so forth, or xn is equals to xn minus 1 minus f of xn divided by f prime xn. And the stopping criteria are the 3 criterias: either xn minus 1, the absolute value of that is less than the error value, or absolute value of the function value of the nth step is less than the threshold value, or the total number of iterations is max iterations. Does that make sense, guys?
Yes, it does, Professor.
Let me know if you have any questions, guys.
Yeah, just
Professor, do we
Yes.
use all three stopping condition or just pick one?
Generally two, to be on the safe side. And out of that two, this has to be there. This is must. And you can pick any one of these two. Either one of these two and one of that. So generally that is basically the standard practice for stopping criteria. Make sense, guys? You can use only one as well. You can check. I mean, that's what we are going to do in the MATLAB class assignment, or basically the class exercise that we are going to do in the next lecture. We are going to use 3 or 2 and then see how it is going to affect the root finding ability for the Newton's method. Is everybody with me so far?
yeah.
Yes, Professor.
Yeah. Any questions? Okay, if not, then we will actually wrap up our today's discussion with another method, which is called secant method. So secant method, you will see it is very similar to Newton's method, except that instead of one initial starting point, you start with 2 values or 2 starting points. Again, I'm arbitrarily drawing function. This is your x-axis, this is a y-axis, or f of x function value at x. So in secant method, you start with x0, x1, and f of x0, f of x1. So what happens that when we are doing, let me actually write it. This is secant method. When we are doing Newton's method, what we are actually doing is we are finding the root of the equation for successive iterations using this formula. Xn equals previous value minus f of x n minus 1 divided by f prime. Am I writing it correctly, guys? So, okay, there is some correction here. So it is n minus 1, not n. F prime x n minus 1, not n, because xn is equals to xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1. So previous point, data points. So this is all x1 is x0 minus fx0 divided by f prime x0. So it is basically fxn minus 1, f prime x minus n minus 1. So that is a small correction you can make it here. So I'm writing down that equation again, f prime x n minus 1. So that is what we have in Newton's method. So what happens that in Newton's method, you have to for every step, you need to evaluate this f prime of x. So let's say if your f of x is sine x plus natural logarithmic of x plus x raised to power 5 times cosine x. So you will see if to find f of prime of x itself requires a lot of computation effort, So you need to take the derivative of this function. You need to take the derivative of natural logarithmic of x. You need to take the derivative of this using chain rule. So you have to take this derivative and then you have to evaluate that f prime of x at a specific value. So for every step, you are going to evaluate the value of f derivative x or f prime x. Whereas in secant method, what you actually do is you start with 2 initial guesses. Now it is the same as the bracketing method where you start with two initial guesses, but the main difference is that initial guesses need not bracket the root. So there is no requirement this x0 and x1 should be opposite side of this root. So in bracketing methods, which you remember, x0 and x1, a and b are on the opposite side of the root. But here you are not, it is not constant. You can pick any value, successive values of x0 and x1, and you can find the function value at that. And by using these two values, you can find the slope of the function at, or derivative of the function at x1. So f prime, or you assume that f prime at x1 is given by f of x1 minus f of x0 divided by x1 minus x0. So instead of exactly doing the derivative and evaluating this function, you are approximating that slope of the function at x1 using this simple computation, which is just subtraction of these two numbers divided by the subtraction of these two numbers. That's it. Does that make sense? So eventually for sequence method, the iteration or the formula remains the same, except instead of f prime of this, I'm substituting that with this number. So for secant method, the formula remains the same, minus xn minus 1 divided by f prime of xn minus 1. Now f prime x minus 1 is basically given by this expression. So it will be xn minus 1 minus f xn minus 1. F prime xn minus 1 is given by f of xn minus 1 minus f of xn minus 2, and on the numerator it will be xn minus 1 minus xn minus 2. That's it. So that is what your secant method says. So you start with n equals 2 because you already know x0 and x1. Start your iterations. With n equals to 2 because you already know x0 and x1. These are your initial guesses. Initial guesses or starting points. So secant method requires two starting points, just like your bracketing method requires. If I actually go back and show you the bracketing method. So if you actually remember, when we discuss the bracketing methods basically requires this interval where the root lies between x0 and x1. So x0 is on this side of the root, x0 was on the other side of the root. So you always need 2 points for bracketing methods. So for bisection method, what you are doing, you are basically reducing the interval length by half, and that's how you're reaching towards the root. For the false position method, if I show you the false position method, again you have two starting points which brackets the root. One is on the left hand side, another one is on the right hand side, and you are basically reaching towards the root by finding the straight line that joins these two endpoints. So that's how the bracketing methods work. When we were doing the Newton method, you remember for the Newton method, we actually need only one starting point, one initial guess. And from that initial guess, we are actually reaching towards our actual root using this algorithm, where I found that x1 is dependent on the first guess, then x2 will be dependent on the previous estimate of x, and so on and so forth. And that's how I'm basically reaching my x and the nth value of x. Similarly, for secant method, I need the initial guess, but I need two guesses, and they do not need to be on the opposite side of the roots. They can be on either side of the root. So you start with this and you plug the value of n equals to 2, and everything will be just using this specific expression. You can keep on doing the iteration. From n equals to 2, you can go to n equals 3, 4, 5, 6, and how long you have to go, you will basically use the same stopping criteria we just discussed a while ago.
So Professor, for the secant method, we pick 2 points that are either right of the root or left of the root?
it can be anywhere. It can be also, it can be on both other side as well, because you are not in anymore required to find the two values which are on the other side of the root. So you can start with any random 2 points, successive points basically.
Okay.
You can start with 2, 2.5, 3, 5, 5, 7, whatever the value you select, that you can start.
Okay. Thank you.
Okay. Any questions so far, guys?
No. Can you please show the last portion?
The last one, which is, which one? This one or this one?
Yeah, that one. I'm missing that one. Thank you.
This one. So what I was saying, that in this method, you actually need 2 starting points as an initial guess. And once you start with this, you are writing your algorithm, which, or the loop, if you're using for loop or while loop or whatever loop you're using, for that loop, the counter starts at 2. So when the counter starts at n equals 2, then you need x1 here, x1, x0. x1 and x0 are already known to you. If you x1 and x0, you have already assumed as starting points. So everything will be known from n equals 2 onwards. So you can start with n equals to 2, then n equals to 3. You keep on doing that, and you will probably reach a specific number, let's say x7, where the stopping criteria is satisfied. Say x equal to 7 is less than epsilon tolerance. So you stop at this. This will be the value at which you will stop. Does it make sense?
Yes, thank you.
Yeah, okay, thanks.
Professor, so
yes,
all these
ahead.
methods, there's only one root inside the interval, right? What if there like more than one root? Or do we know there's only one root?
So yeah, there is no way that you can find there is only one root, because you do not know whether, for open methods, it is always the case that the function may not be looking like this, but it may look like this. So in that case, you start with this value as the initial guess, and you may converge to that root, or you actually go to this root. So these are all the roots of that, and there is no guarantee that you can basically reach any one root. So it depends on the generic nature of the function. So there is no rule or no method or no way to actually move or reach to only one roots.
So like we don't know which root we converge to, if there's multiple root. Okay.
Yeah, it can have multiple roots. So if, for example, you start with a bracketing method, and in that case you actually pick an interval which actually which brackets this root. So in that case, you are going to converge to that root. Okay, but if your bracketing interval is this whole segment, then you do not know whether you are going to be when you are reducing the interval length by half, you do not know whether you are finding the root in this interval or you are going to find the root in this interval, because both of this interval has the sign changes of the function happening. Does it make sense?
Yes.
So you can use a bisection method, and for every root sign change, you can save the data points and keep on doing the bisection method again to actually close on the specific root. But there is no guarantee that you know how many roots are present for that equation within that interval.